Hi everyone and welcome to Ancients. In this video, we will explore in detail how electricity is generated in a wind turbine. A wind turbine converts the kinetic energy of wind into electrical energy. In this video, we will examine a 2-megawatt wind turbine. The number of homes this turbine can power varies significantly by region, depending on average electricity consumption. A single 2 megawatts unit operating under average wind conditions can power approximately 400 to 600 homes in the United States, 1,000 to 1,500 homes in Europe, or around 4,000 to 5,000 homes in India for an entire year. Physically, this turbine is massive. It stands on a 90-meter tower and has a 90-meter rotor diameter, reaching a total tip height of 135 meters. To put that in perspective, that is roughly the height of 35 homes or a 40-story building. The blades rotate at speeds between 10 and 19 revolutions per minute, depending on wind conditions, usually settling around 14 to 17 revolutions per minute for rated power output. But how does the wind actually force these massive blades to rotate? A wind turbine blade functions much like an airplane wing. It is designed to generate lift when wind flows over it. The blades are shaped as airfoils, which are carefully engineered cross-sectional profiles optimized for wind energy conversion. When wind hits the blade's cross-section, the air travels faster over the curved upper surface and slower beneath the flatter lower surface. According to Bernoulli's principle, this creates low pressure on the upper surface and higher pressure below. This pressure difference generates an upward force called lift, which moves the blade toward the low-pressure region. Lift force is perpendicular to the wind direction and is the primary force that rotates the blade. Drag force opposes the motion of the blade. Drag is caused by friction and pressure differences along the blade surface as air molecules interact with the blade. Now, let's understand the blade's terminology to better comprehend its shape and function. The blade root is the closest section of the blade to the hub. It attaches the blade to the rotor hub and transmits all loads, including bending moments, torque, and gyroscopic forces, to the main shaft. The blade tip is the farthest end of the blade, traveling at the highest speed. The airfoil is the cross-sectional shape of the blade, optimized for lift generation. The leading edge is the front edge that encounters the wind first. The trailing edge is the rear edge where airflow leaves the blade surface. The chord is the straight line distance between the leading and trailing edges. The pitch angle is the angle of the blade relative to the plane of rotation, which is adjustable to control power output. The rotor blade is thick and very wide at the root, tapering to be thin and narrow at the tip. The blade functions as a massive cantilever beam. Internal bending stress is maximum at the fixed root and gradually decreases along its length, becoming zero at the free tip. To withstand this maximum bending moment, the blade requires its largest and strongest cross-section at the root. Tapering also serves critical aerodynamic functions. The blade root travels the slowest while the tip travels the fastest. At a 90-meter rotor diameter spinning at 15 RPM, blade tips can achieve speeds of approximately 210 to 255 kilometers per hour. The wide, thick root section, which moves slower, is designed to generate high startup torque to begin spinning the rotor in low winds. The narrow tip is designed to minimize aerodynamic drag at its very high speeds. Blade tips move faster through the air than sections near the hub. Wind hits different sections at different angles. Therefore, the blade is twisted, typically 10 to 20 degrees from root to tip, to maintain an optimal pitch angle along its entire length. This twist improves efficiency and prevents the blade from stalling. To generate the 50 Hz electricity required by the electrical grid, the generator must rotate within a limited speed range, approximately 1400 to 1600 RPM for a typical 4-pole generator. However, wind speed constantly varies. A pitching mechanism is used to rotate the blades around their longitudinal axis, allowing them to capture more or less energy and maintain optimal rotor speed. An integrated bearing mechanism with an internal gear ring is present at the blade root. The outer ring of the bearing is bolted to the hub, while the inner ring is bolted to the blade. This bearing allows the blade to rotate around its own axis while maintaining a secure mechanical connection to the hub. A synchronous pitch motor mounted in the hub with a rated speed of approximately 1500 RPM is used in the pitching mechanism. However, its torque is insufficient on its own to rotate the massive blade against wind forces. A multi-stage planetary gear system is employed to multiply torque and reduce speed. In this model, a two-stage planetary system is used with individual reduction ratios of 5 and 6, creating a total reduction ratio of approximately 30. A large internal ring gear is then driven by a spur gear, providing final gear ratio around 350. Pitch motors operate automatically depending on wind conditions, with each blade independently controlled for optimal performance and load balancing. Wind turbine blades are not perfectly rigid. They are flexible. Under high wind speeds, the aerodynamic thrust pushes the blades backward, causing them to bend toward the tower. If the rotor is perfectly horizontal, a strong gust could bend the blade tip enough to hit the tower as it passes the lowest point. By tilting the rotor shaft upward, the blades rotate in a plane that leans away from the tower. This increases the distance between the blade tip and the tower wall, known as tower clearance, ensuring that even when the blades flex under maximum load, they remain safe. For a standard 2 megawatt wind turbine, this tilt angle is typically between 4 degrees and 6 degrees. The bed plate is the critical structural component that creates the rotor tilt. Think of it as the chassis or the rigid floor frame of the nacelle. While the tower stands perfectly vertical, the bed plate acts as a structural wedge. The bed plate is a massive piece of cast iron or welded steel. It is not a flat slab. It is designed with a specific geometry to create the tilt. The bottom of the bed plate is flat and horizontal. The top surface, where the main shaft and gearbox sit, is machined at an incline. When you bolt the main bearing and gearbox to the bed plate, they automatically point slightly upward. This avoids the need for complex bent shafts. The components are straight, but the table they sit on is slanted. The hub is not a simple shape. It is a complex, hollow 3D structure with 3 large, precision-angled openings for the blade bearings, 1 opening at the front, and 1 large opening at the back for the main shaft. The internal structure has walls and ribbing to direct the immense structural loads while leaving enough space for the pitch systems. The hub transfers the mechanical energy generated by the rotating blades to the main shaft. It is typically made of cast iron or ductile iron, weighing approximately 17 to 18 tons for a 2 megawatt turbine. The hub bears various forces from the blades, including torque, bending moments, and gyroscopic forces caused by varying wind conditions. A control unit within the hub, called the hub control unit, controls the blade pitch mechanism and supplies power to the pitch motors through slip ring connections. The center of the rotor is a flat, blocky piece of metal. Wind would hit this flat surface and create drag. The nose cone, also called the spinner, is the aerodynamic cover attached to the front of the rotor hub. While it looks like a simple cap, it performs several critical functions for the turbine. It is typically made of lightweight fiberglass to resist corrosion and weather. The spinner's curved shape guides the wind smoothly outward toward the blades, improving the overall efficiency of the turbine. It acts as a weatherproof shield. Inside the spinner is the pitch system. The spinner keeps rain, snow, salty air, and lightning away from these expensive components. The main shaft transfers the low-speed rotational force from the hub to the gearbox. The main shaft is mechanically connected to the hub via bolts. It is supported by 2 main bearings that keep the shaft aligned and stable during rotation. These bearings absorb mechanical loads, including radial forces, axial forces, and overturning moments, protecting downstream components like the gearbox from excessive stress. A hollow shaft design is employed for the main shaft. This design provides a high strength-to-weight ratio while reducing material usage. The hollow interior also serves as a passageway for electrical wiring and data cables for pitch motor control, creating an electrical and data connection between the nacelle and the hub. A shrink disc coupling connects the main shaft to the gearbox input shaft. The gearbox has a hollow input shaft, and the main shaft is inserted into it. A shrink disc coupling functions as a high-strength, keyless mechanical connection used to lock a hollow shaft onto a solid shaft. A shrink disc fits on the outside of a hollow shaft hub. It squeezes the hollow hub so tightly that it grips the solid shaft inside it, effectively fusing them into a single unit during operation. A standard shrink disc consists of 3 main parts. First, a ring with a tapered outer surface called the inner ring. Second, two rings with tapered inner bores that match the angle of the inner ring, called the outer rings. And third, high-strength bolts that pull the outer rings together. The screws pull the outer tapered rings towards each other. As the outer rings slide up the tapered slope of the inner ring, the reduced volume forces the inner ring to contract. This contraction exerts immense radial pressure inward on the hollow hub. The pressure reduces the diameter of the hollow hub slightly, clamping it down onto the solid shaft. This creates a friction fit around the entire circumference of the shaft. The generator requires approximately 1500 RPM to generate 50 Hz electricity, but the rotational speed from the wind turbine rotor is only 14 to 17 RPM. Therefore, a gearbox with the final gear ratio of approximately 100 is used to achieve the required rotational speed. In this model, a three-stage gearbox is employed, featuring one planetary stage and two parallel-axis helical gear stages. A planetary gear system is preferred for the high-torque input stage because the load is distributed among multiple planet gears, typically 3. In this model, the planetary stage has a gear ratio of 6, and the parallel helical stages have ratios of 5 and 3.3. Overall, the gearbox increases speed by approximately 100 times relative to the input speed. In this gearbox design, a hollow shaft extends from the input through to the opposite side of the gearbox. This hollow shaft rotates with the input shaft and has no contact with other gear shafts. Cables from the hollow passage of the main shaft pass through this gearbox hollow shaft, providing a pathway for electrical wiring to reach the other side of the gearbox. A slip ring assembly is directly connected to the hollow shaft extending from the gearbox. This equipment enables the transfer of electrical power and data signals between rotating and stationary components. The slip rings rotate with the shaft, while stationary carbon brushes slide on the rings, maintaining continuous electrical contact. Wires connected to the brushes are routed to the nacelle control unit. Through the slip ring system, power for the pitch motors and data signals from the hub sensors are transmitted to and received from the nacelle control unit. A composite disc coupling is positioned between the gearbox output shaft and the generator input shaft. This coupling connects the gearbox to the generator, enabling the transfer of rotational power while accommodating multiple types of misalignment between the shafts. The composite disc packs provide flexibility to absorb misalignments while remaining torsionally stiff to efficiently transmit torque. Critically, this coupling electrically insulates the gearbox from the generator. The non-conductive composite material prevents damaging electrical currents from leaking into the gearbox bearings and gear teeth, which could cause premature wear and failure. A doubly fed induction generator, or DFIG, is used in this wind turbine to generate electricity. It is a variable speed generator that produces constant voltage and frequency even when operating at variable rotational speeds. In a DFIG configuration, the stator is directly connected to the electrical grid, and the rotor is connected to the grid through a back-to-back power electronic converter. Slip rings with carbon brushes are used to connect the rotor windings to the power converter. The converter can inject power into the rotor or extract power from it at a precise slip frequency, depending on operating conditions. This system allows the generator to operate across a wide range of speeds, typically plus or minus 30% of its synchronous speed, and still produce a stable 50 Hz output frequency. DFIG operation modes include sub-synchronous operation. When the turbine spins slower than synchronous speed, the power converter injects power into the rotor through the slip rings and brushes. This additional rotor excitation allows the generator to produce grid frequency power even at lower speeds. Next is synchronous operation. At 1500 RPM, the rotor requires minimal excitation, and nearly all power is generated through the stator. Finally, supersynchronous operation. When the turbine spins faster than synchronous speed, the generator induces excess power in the rotor windings. This excess power flows out through the slip rings and brushes to the converter, which feeds it back to the grid. Because only approximately 25 to 30% of total power flows through the converter, the DFIG system is more cost-effective and efficient than full converter systems. Several technical terms describe wind speed limits for wind turbine operation. First is cut-in speed. This is the minimum wind speed at which the turbine blades begin rotating and the turbine starts producing usable power. This is typically 3 to 4 meters per second. Second is rated wind speed. This is the wind speed at which the turbine generates its rated maximum power output of 2 megawatts. This is typically 11 to 16 meters per second. Third is cutout speed. This is the maximum wind speed at which the turbine is allowed to operate safely. Above this speed, the turbine automatically shuts down to prevent damage. This is typically 21 to 25 meters per second. Now we will examine how the pitch control system operates across different wind speed ranges. Below cut-in speed, or less than 3 to 4 meters per second, wind speed is insufficient to generate power. The blades are pitched to approximately 90 degrees, or fully feathered, with their leading edge facing directly into the wind. This minimizes aerodynamic lift and prevents unnecessary rotation that could cause wear on components. Between cut-in and rated speed, the pitch angle is maintained at approximately 0 degrees. This is the most aggressive power capturing configuration, maximizing lift to extract maximum available power from the wind. From rated speed to cutout speed, the pitch angle is actively adjusted, typically between 0 and 30 degrees. This is the most active phase for the pitch system. The controller progressively increases pitch angle to spill excess wind energy, maintaining constant power output at the rated 2 megawatts. This prevents overloading the generator and drivetrain. Above cutout speed, or greater than 25 meters per second, the turbine blades are fully feathered to 90 degrees to stop the rotor aerodynamically. After the rotor has slowed sufficiently, mechanical brakes are applied as a secondary safety measure. The hydraulic brake system is located on the high-speed shaft between the gearbox and generator. Under normal operating conditions, the brakes remain disengaged. Hydraulic pressure from a hydraulic power unit keeps the brake calipers released. When wind speed reaches cutout speed, the blades are first slowly feathered to 90 degrees, bringing the rotor to a stop aerodynamically. Only after the rotor speed is sufficiently reduced are the mechanical disc brakes applied to hold the rotor stationary. The brakes are also used for emergency shutdowns such as pitch system failure, grid disconnection, or component overheating and during maintenance operations. The brake system is fail-safe. Springs apply braking force by default, and hydraulic pressure is required to release the brakes. All components must operate continuously over a 20 to 25-year lifespan, making effective cooling essential. The gearbox and generator are the primary heat-generating components in the nacelle. For gearbox cooling, an oil-to-air heat exchanger or radiator is typically mounted on top of or at the rear of the nacelle. A fan draws air from inside the nacelle through the radiator and exhausts it outside. This removes heat from the gearbox oil while preventing hot air from re-entering the nacelle. An air-to-air heat exchanger is used to cool the generator. It consists of two independent, sealed air circuits. First, the internal loop. A blower circulates air inside a closed loop through the generator. This internal air absorbs heat from the generator windings and components, then passes through one side of the heat exchanger where it is cooled before being recirculated through the generator. Second, the external loop. Separate blowers continuously draw air from inside the nacelle, pass it through the other side of the heat exchanger, and then exhaust it outside the nacelle. This transfers heat out of the system without allowing external contaminants like dust, moisture, or salt to enter the generator. This closed-loop design protects the generator from environmental contamination while efficiently dissipating heat. Wind direction changes continuously. A wind vane or anemometer, mounted on top of the nacelle, constantly monitors wind direction. The yaw system rotates the nacelle to face directly into the wind direction for maximum energy capture. A large diameter yaw bearing is positioned between the tower top and the nacelle base. The inner ring is bolted to the nacelle base, while the outer ring is bolted to the tower and features an external gear ring. Multiple yaw motors, typically 4, drive the yaw system. These motors are similar to pitch motors but require even greater gear reduction to generate the enormous torque needed to rotate the nacelle against wind loads. In this model, each yaw motor uses a multi-stage planetary gear system. 3 planetary stages with ratios of 5, 6, and 6 create a combined ratio of 180. The final spur gear engaging the yaw ring provides an additional reduction of 15, resulting in a total speed reduction gear ratio of approximately 2700. Sometimes, due to changing wind directions, the nacelle completes full rotations to stay aligned with the wind. When 2 rotations are completed, wires from the nacelle to the tower bottom can get tangled. When this happens, the entire turbine shuts down, and the yaw system rotates the nacelle back to its original position. The yaw braking system prevents unwanted nacelle rotation. Brakes are applied by default using spring force. Multiple brake calipers are bolted to the nacelle, with brake pads pressing against a flange on the tower. A separate hydraulic power unit supplies pressurized fluid. During yaw movement, the hydraulic system pressurizes the brake calipers, compressing the springs and releasing the brakes. When yaw adjustment is complete, hydraulic pressure is released, and springs automatically reapply the brakes, locking the nacelle in position. Towers are designed to support the immense weight of the nacelle and rotor while withstanding enormous wind loads, bending moments, and vibrations. Like the blades, the tower is tapered. Bending moment increases toward the base, so the tower diameter is largest at the bottom and gradually decreases toward the top. The tower is a hollow tubular steel structure constructed from multiple segments, typically 3 or 4 sections for a 90-meter tower, bolted together with large flanged connections. Tower weight for a 2-megawatt turbine ranges from approximately 190 to 255 tons depending on height and design. The tower contains an internal ladder and a service lift for technician access to the nacelle. Platforms at segment connections allow safe climbing rest stops and facilitate inspection of flange bolts. To protect against corrosion, the steel structure is coated with a highly durable multi-layer paint system designed to resist corrosion, rain, UV radiation, and environmental wear, providing a 20 to 25-year service life. Power cables, control cables, and data cables from the nacelle run down through the hollow tower interior to the tower base. A main control unit is located at the base of the tower, typically in a separate enclosure or control room at ground level. This control unit monitors and controls the entire wind turbine operation, including pitch control, yaw control, braking systems, and grid connection. The generator in the nacelle produces electricity at 690 volts. This voltage is too low for efficient long-distance power transmission. Therefore, a step-up transformer is installed at the tower base, which converts 690 volts to 33 kilovolts. The transformer is typically pad-mounted near the tower base for easy access and maintenance. To support the tower, a massive foundation is constructed. A wind turbine foundation is engineered to anchor the turbine and safely transfer all loads, including the weight of the tower, nacelle, and rotor, as well as enormous lateral forces and overturning moments from wind pressure and rotor rotation, to the ground, ensuring stability and long-term structural integrity. This foundation type is called a gravity foundation. It is a massive, shallow, reinforced concrete structure that uses its own immense weight to hold the turbine stable and prevent the tall tower from toppling over. A typical gravity foundation for a 2-megawatt wind turbine is approximately 15 to 20 meters in diameter and 2 to 3 meters deep. The foundation contains a precisely engineered steel anchor cage, a complex assembly of reinforcing bars, set into the center before concrete is poured. This anchor cage contains the large anchor bolts that connect the foundation to the base of the tower. Wind turbine systems face significant risk of lightning strikes due to their height and exposure, especially in areas with high lightning activity. A single lightning strike can cause catastrophic damage to blades, electronics, and other components. Separate lightning receptors are installed at each blade tip. These receptors are designed to provide a preferential attachment point for lightning strikes. The receptors are connected to down conductors, which are heavy gauge cables embedded inside each blade. These conductors run through the blade interior, through the hub, down the main shaft, and through the tower to the grounding system. An additional lightning arrestor is mounted on top of the nacelle to protect nacelle components and equipment. All lightning conductors are connected to a comprehensive grounding system at the tower base. A wind turbine's grounding system is a critical safety network designed to provide a safe path for dangerous electrical currents, from lightning strikes or electrical faults, to flow into the earth. The grounding electrode for a 2-megawatt wind turbine is integrated directly into the turbine's concrete foundation. This system is called a foundation earth electrode. The primary grounding electrode is the interconnected network of steel reinforcing bars embedded in the concrete foundation. Using special clamps and welding, this rebar cage becomes one massive, electrically continuous conductor. The large total surface area and intimate contact with concrete and surrounding soil make this an extremely effective electrode for dissipating electrical energy. The steel foundation rebar is connected to a ring electrode, a continuous copper or copper-clad conductor, installed around the foundation perimeter, typically buried 0.5 meter to 1 meter below grade. Multiple vertical ground rods are connected to the ring electrode. These rods, typically 2 to 4 meters long, are driven deep into the ground to reach lower soil layers with better conductivity, enhancing the grounding system's effectiveness. This comprehensive grounding system ensures that lightning strikes and electrical faults are safely dissipated into the earth, protecting personnel, equipment, and structural integrity. These remarkable machines represent decades of engineering innovation, delivering sustainable power to thousands of homes while operating reliably for 20 to 25 years in challenging environmental conditions. Thank you for watching the video. If you found this detailed exploration valuable, please like, subscribe, and share to support more technical educational content.